Okay, so it's 4 o'clock by my watch here. So do you mind if we get started? Go for it. Okay, cool. So thanks everyone for joining us here virtually for this seminar. We're very happy to have Professor Brian Fields, join us from the University of Illinois. Brian is a world expert in lots of subjects in high energy astrophysics, including Big Bang, supernova explosions like we'll hear about today, as well as cosmic rays and various other processes where nuclear physics, particle physics, and astronomy collide. Brian got his PhD from the University of Chicago just a couple of moons ago. Then he went to the Institute for Astrophysics in Paris, and then he moved to the University of Notre Dame. So he went from Notre Dame to Notre Dame. He allowed me to use that joke, by the way. Okay. Then he did another short stint postdoc at the University of Minnesota, and he's been faculty at University of Illinois for since he moved there from Minnesota. So, as I mentioned, Brian is a world expert in lots of areas of high energy astrophysics, cosmology, and particle physics. In addition to his the many interesting papers and research he's done through the course of his career, if you read his website, you'll see he's won many teaching awards at the University of Illinois. And he was also elected as a fellow of the American Physical Society just a couple of years ago. So it's a real pleasure to have Brian here. This looks like a very interesting and exciting talk. Hopefully we'll not be scared by the end of it. But so let me turn it over to Brian now to talk about supernova and near Earth explosions. So go ahead.
Great. Well, thank you, Louis, for that great introduction, and thank you all for coming. And I appreciate you rolling with me on having to do this over Zoom. I'm particularly happy to be talking to you at Texas A&M. I have 2 cousins who are diehard Aggies, and you have greatly raised my credibility with my family. So thank you very much for that. And indeed, what I'm talking about today will go from the deep ocean to the moon to the stars. Talking about what happens when stars attack. And I don't mean, an ill-behaved Hollywood celebrity. I mean real astronomical objects, real supernova explosions. And so this covers a lot of subjects to which A&M faculty have made important contributions. And we'll see that nuclear physics, and particularly nuclear experiment, are crucial for the data that allow this to even be a subject. So without further ado, then. Here's the game plan. So we're going to see that radioactivity is an important part of the subject, and we're interested in radioactivity from near-Earth supernova explosions. We'll explain why that's the thing we're interested in. So to make sure we're all on the same page, I'll first talk about supernovae and what they're like. And what happens if they're near the Earth. If they're near the Earth, they're a unique laboratory, but also can pose a unique threat. So I'll talk about the opportunities and the threat. And then the signatures. So if we have an explosion, astrophysical explosion near the Earth, how could we tell? And the spoiler is it's going to be radioactivity that are crucial. And then, and amazingly, we'll see that there actually is real evidence that this has occurred. We actually have such data. And then I'll finish up by talking about the implications of what does it mean that we have this evidence that more than one supernova exploded near the Earth recently. And the implications are for supernova, the origin of the elements, but also for the Earth's neighborhood in space, and even beyond that. So with that, let's begin by talking about supernovae. So we have some experts in your department. So I know many of you know a lot about supernovae, but to get us all on the same page, I just want to draw your attention to the aspects of supernovae critical for the story I want to tell today. So first, let's talk about how you get a supernova in the first place. And I'm particularly interested in core collapse supernovae, the deaths of massive stars. And so before the star dies, it has to live. So what's the life of a massive star like? And so for the purposes of this talk, a massive star is something like 8 times the mass of the sun or more at birth. And those are pretty rare objects. And like all stars, massive stars are born in cold clouds of gas. The cold part is important, so they don't have a lot of thermal pressure, and so they can't overcome the gravity of the self gravity of the cloud, and they collapse. Um, and it's an important thing to appreciate is that massive stars are social, so they tend to be clustered at birth. So if you have one massive star, you probably have several, and they also tend to be born in binary. So massive stars almost all have binary partners, and many times the binary partner is another massive star. And so yeah, here's the Orion Nebula, and this is a nearby star-forming region. You can see it with your naked eye. And the trapezium here, these 4 bright stars, are all massive stars, all destined to become supernovae. And then, once the star is born, as it lives its life, for all stars, their lives are a struggle against their own gravity, the inexorable pull of their own gravity, trying to make the star collapse to a black hole. Like all other stars, massive stars begin by fusing hydrogen to helium in their core. That makes them nice and hot and pressurized, and that pressure is able to, that outward pressure gradient is able to fight against the inward gravity, and the star is stable. And then as a massive star, it undergoes multiple stages of burning at its core, first hydrogen to helium, then helium to carbon and oxygen, and so forth, until the star reaches the stage where it has an iron core surrounded by layers that are burning that are sort of recapitulating the earlier eras of core burning silicon and oxygen and so forth. And so the star has this wonderful onion skin structure that kind of remembers its history. But once the star has an iron core, then basic nuclear physics comes into play, because that's the end of the road for fusion. That is to say that to fuse iron, first of all, is very difficult because the Coulomb barrier becomes so strong because of the high electric charge. But also, iron has the highest binding energy per nucleon. So when you fuse towards iron, that releases energy. That's exothermic. But to fuse iron, it is possible, but that's endothermic. It's no longer an energy source. It no longer can heat the star. And so once we have an iron core, that's the end of the road. And so the iron core builds up and builds up until, but that too is a losing game, because once it exceeds the maximum mass to be stable, the Chandrasekhar mass, then it collapses and the star dies, and the result is an explosion. So it runs out of fuel, the star collapses, and then the star explodes. And then most of the star is ejected. So most of these layers full of this nice new result of all this nuclear burning, those are flung into space at a few % of the speed of light. And we see these amazing fireworks like you see here in Supernova 1987A, as well as a blizzard of neutrinos. All right, so that's the basic story, but I want to emphasize one other aspect of supernovae that are very important. Supernovae are element factories generally, and I'm also interested in the fact today that they're radioactivity factories. So as they go through their burning stages, supernovae make elements. Mostly they make stable things. And so their main products are alpha nuclei, things you can think of as little clusters of helium-4s, because they begin making helium. And so things like carbon-12, oxygen-16, and so on, up to calcium-40, and also titanium-44. And then as the star is exploding, it goes to very high temperatures and burns to make the most thermodynamically favorable thing. It reaches nuclear statistical equilibrium, we say, and that then makes iron and the iron peak elements. And that's not just some theorist's dream. We see this because what I'm showing you here is an image of the Cas A supernova remnant. So this is an explosion from 300 years ago. And then what you're seeing here is an X-ray image, and it's color-coded, so you can look at the line emission to take apart the different elements here, and we see, lo and behold, it's full of iron, as befits the iron peak, also lots of silicon and magnesium, good alpha elements, but then the thing I want to emphasize is there's also, as shown in blue here, there's this radioactive titanium. This, it turns out, is what you're seeing is a nuclear line from the decay of titanium-44, which has a half-life of 60 years. So this thing is 300 years old, so it's already had multiple half-lives, but there's still some titanium-44 lying around. And obviously, with a lifetime this short, none of this titanium could have pre-existed the star, which lives for millions of years. So what this is telling us is this this definitely is these radioactive titanium elements came directly out of the exploding star. In fact, they were produced in the explosion, and this is a direct proof of the production of elements in stars. Not a surprise, we have other reasons to believe that, but it's just nice to see such a beautiful direct proof. And it also shows, from my point of view, it's also showing that supernovae indeed make radioactivity. So this is a relatively short-lived radioactivity compared to what I'm interested in. I'm interested in what I would call, say, medium-lived, which is to say sort of million years to multiple million-year lifetimes. And we'll be particularly interested in iron-60, but I've got a list of other things that are cool: aluminum-26, technetium, samarium. It is also possible, but not guaranteed, that supernovae make the R process, which is this way of making the very heaviest elements. And this is through a rapid capture of neutrons. So there need to be a big blast of neutrons. And supernovae probably make some amount of R process, but we're not sure how much. And there's also neutron star mergers. But if supernovae make the R process, there are additional radioactivities that are of interest, and we'll be particularly interested in plutonium today, plutonium-244. So the main thing, supernova radioactivity factories, and these radioactivities will be expelled from the supernovae and thrown into the environment along with the stable elements of which we actually are made. Okay, great. So that's the big picture of supernovae. Now let's take the problem closer to home and talk about what happens if we have a supernova near the Earth. This is supernova 1987A. This isn't actually what I mean by nearby. That's the most recent nearby supernova, but this wasn't even in our own galaxy. And that's not what I mean by nearby. I mean something much closer than that. So the idea here, that is, if we have a supernova near the Earth, there comes a point where it's not funny anymore. A nearby supernova explosion can actually be a cosmic weapon of mass destruction. And in these perilous days, WMD are nothing to joke about, but this really is the appropriate standard of comparison. But I want to emphasize, we live in a star-forming galaxy that today is still giving birth to stars of all masses, to include massive stars, which are destined to explode. So as citizens of a star-forming galaxy, nearby supernovae are an inevitable fact of life. It's not a question of if a supernova will explode near us, it's a question of when. But when depends on how far. So let me give you a sort of simple sort of back of the envelope calculation, which is fun to do. I urge the students to give it a try. So we want to know if we're sitting someplace in the disk of our galaxy. This is a not to scale sketch of our disk that we live in. And we're sitting someplace in our disk. We put a sphere of radius d around us. And I want to say, what's the rate of supernovae inside that sphere? Because I want to assess the threat. And the idea is supernovae are going off throughout the galaxy at some rate, about 2 to 3 per century. And I want to know if they're going off uniformly throughout this disk, what's the rate they're going on just in this little sphere around us. And it turns out that's not that hard to work out. The rate just inside the sphere is the total rate times the volume fraction of the sphere relative to the full disk. And if you punch in the numbers, what you'll find is that for a distance 50 parsecs away, which is very close. The nearest star is a little over 1 parsec away. So that's sort of a typical spacing between stars. 50 parsecs is very close. That's a very nearby neighborhood. The Orion Nebula I showed you is 4 further. This is very close. So a 50 parsec supernova, you expect that to happen about every 15 million years, which is short compared to, say, to the time it takes a grad student to get a PhD. So you don't have a PhD student around for this, but this is very, it's long compared to the lifetime of a PhD, short compared to the age of the Earth. So over the age of the Earth, we expect to have many events at this kind of distance. In fact, we can even expect to have events down to 10 parsecs, which is the kill distance. So if we have a supernova down to 10 parsecs, that actually becomes a threat to the biosphere of the Earth, a threat to life, and potentially could cause a mass extinction. So once you appreciate the numbers, then this problem is not just an academic one. It becomes really interesting to ask, what happens if you have a nearby supernova, and how could we find out? And just to give you a second, so that I just have some wonderful undergrads working with me. Some were doing the calculations I was just telling you about, and some are working on the aspects of the damage. And it turns out the damage a supernova does, it's a whole story, but just to summarize, there are three basic phases. It's a triple whammy. The first thing is when these things explode, they make these incredible optical fireworks, but they also emit, invisible to the naked eye, gamma rays. And those gamma rays, it's the ionizing radiation that's the problem. The gamma rays are the first bit of ionizing radiation that hits, and they strip ozone from our stratosphere and leave us vulnerable to UV radiation from the sun. And I don't mean like a little ozone hole, I mean strip it off, clean. And then over 5 to 10 years, the Earth will recover from this because this all happened in the first year or so. But then several years later, if the supernova is surrounded by a dense medium, for example, if it had a wind that blew away material that the explosion then runs into, there then afterwards, after a delay, when the blast crashes into this wind, it gets heated up to million-degree temperatures and it emits X-rays. And if it's X-ray bright, those X-rays can also be very damaging and can again strip the ozone layer clean. And then finally, many thousands of years later, when the supernova blast encompasses the Earth, then we get baked by cosmic rays, high energy, mostly protons that are accelerated by this supernova remnant, and then we're baked for a very long time. And so all of these things strip the ozone from the upper stratosphere, and then we get baked by the UV from the sun. And big critters like us would put on our hats and sunblock, but if you're a phytoplankton, there's nothing you can do about this. And the idea is that it kills the bottom of the food chain and the damage propagates up. All right, good. So that's why a nearby supernova is bad. So how do the supernova come to arrive, and how can we tell? So first, let me give you a sort of bird's eye view. So what we're seeing here is a sort of very simplistic simulation, just to get you in the mood, on sort of interstellar scales. So I'm having the supernova blow up where it says 0, 0 here. I'm showing you a little simulation where I have a supernova blow up in an idealized way, in a spherically symmetric way, in a uniform medium, just to give you a sense of the timescales. And you're seeing a density map here, and you see what the supernova is doing is it's making this blast that has a high density shell and this hot rarefied interior. And as the movie loops around, you can see I drew a circle at 10 parsecs, which is the kill distance, and you see it kind of wash over any poor observers there. And you may not be able to see the time scale very well, but it takes sort of tens of thousands, depending on the conditions, up to 100,000 years to sort of for the blast to come by. So when the blast comes by, it's not an overnight thing. It lasts for thousands of years. Okay, so that's what it looks like, sort of the big picture, the interstellar scales. Now I want to zoom down to a much smaller scale and see what this does to the solar system itself. And this is work I've done that largely by Jesse Miller, who's now a postdoc, doing more of this work. So now let's zoom into the scales of the solar system. And in the sun, we've got, that's where the sun is supposed to be. So now this is a region where the Earth going around the sun is this little black circle you can barely see. And what I'm showing you here is in the absence of a supernova, there's still the solar wind. So the sun is blowing this wind and the supernova is going to collide into it. And so I'm going to show you a little simulation. It's a supernova at 50 parsecs, which is going to turn out to be an interesting distance, not close enough to kill us. And you should appreciate the simulation is done in an axisymmetric coordinate. So you're supposed to sort of spin it around the sort of vertical axis here to appreciate the three-dimensionality of it. And then we're going to launch a supernova from below. So it's like Jaws. So here we go. So it's 50 parsec supernova, and we're going to launch it. And you see what it does. It blasts back the solar wind, and to make a bubble much more compressed than we have today. And the solar wind comes in to about not quite the distance of Saturn. So that's the solar. So the Earth becomes very close to the supernova material, but the supernova material doesn't actually come all the way to Earth. So it's quite a dramatic effect, and will have serious effects on life. But it's not. It doesn't actually. The Earth itself, which is this tiny little circle here at 1 astronomical unit, the Earth itself isn't inside the blast. So we have the supernova near us. It causes all kinds of mayhem, but we don't actually end up inside the blast. So how can we tell? And it turns out what happens is if the supernova is close, it literally rains its ejecta, its newly formed elements. They literally rain upon the Earth. So here's how it works. So now in a maybe more schematic way, here's another one of these beautiful X-ray images of a supernova. And it sweeps out interstellar matter, as we've seen. The Earth is shielded by the solar wind. This is now a real image of the actual solar wind. These are very much not to scale. And I showed you how the collision works. So as I showed you, if the blast is close enough, it will reach the inner solar system, but not all the way to the Earth. But the elements in the supernova, the heavy elements, most of them rapidly condense from the gas phase into small solid particles, which are dust grains, stardust. And we observe this in supernovae. We see dust forming in supernovae, and it's rapid. It's after months that the dust forms, which is kind of amazing, actually. And these sort of micron-sized particles are found in supernovae, and they have complicated lives, and that's a whole story we can talk about. But the material that's in dust, even though the supernova blast doesn't come all the way to us, it comes very close, and the particles in dust have no trouble traveling the rest of the way, slamming into the Earth's atmosphere. They get atomized, and the stuff eventually finds its way down to the ground and ultimately accumulate in the deep ocean. So that's then what we're going to do. We want to find supernova debris at the bottom of the ocean. That's the game. All right. So far, so good. And so feel free to interrupt if you have questions. So here we go. So now we got the smoking gun. So how do we know? So the idea is maybe we had a threatening supernova millions of years ago. We don't have any today, by the way. Sorry, I should have mentioned this right away. Louis was worried about me scared. There are no threatening massive stars close enough today to be dangerous. So like the stars in Orion are too far away, so we're fine. But if you're interested in your ancestors or your descendants over long time scales, this is important. So if we look back in the geological record millions of years ago, how can we identify whether there was a supernova? So we want to look for a supernova fingerprint that we can find in the geological record. So a sobering calculation is this. I'm calculating this is the surface density of supernova material on the Earth. And this is actually for a 10 parsec supernova, which is a pretty close one, a dangerous one. And even for a pretty close supernova, what this is telling you is that every square centimeter of Earth will have not quite a microgram of supernova material, a microgram. That's not a lot. So this isn't going to be like finding the impactor that hit the dinosaurs. There's not going to be some beautiful visible layer in the geological strata. We're going to have to work harder than this. So that's what this says. It's a tiny bulk signal. So we can't just find it visually. We're going to need to look for isotopes the supernova produced. And we could look for the stable things that supernova produce. What does it make? It makes a lot of oxygen and iron. That's great. But of course, just looking for oxygen and iron doesn't prove anything because the Earth is full of those things. So stable nuclides don't work because the Earth already had plenty of those. This is why I'm so obsessed about radioactivity, though. If we can find live radioactivity, by which I mean radioactive species which have not decayed, and so they're still alive, then that's great because there aren't any left on Earth if their lifetimes are only millions of years. And so the analogy here is green bananas. So like radioactive nuclei, bananas decay over time. And when you find green bananas, that's like live radioactivity, undecayed. And if you find green bananas, certainly in Illinois, then you know two things. First, they were made recently. And second, they were definitely not made here. So something had to bring them. And so it's the same story with our supernova radioactivities. There are green bananas. If we find them, they weren't made on Earth. They had to have been brought here. So that's the game. And we're going to be particularly interested, all kinds of radioactivity are interest of sort of million-year or more lifetime, but we're going to be particularly interested in iron-60, which has a half-life of 2.6 million years. But as I said, there are other species of interest, which we'll get to. All right, so that's the game. We want to now look for live radioactivity at the bottom of the ocean. That's the game. Now, the cost of this is all of the supernova material was already this tiny signal. The radioactivity in the signal is even smaller. That's not even most of what the supernova makes. So now the signal is truly tiny. That's the price of this. Okay, and this is where nuclear physics comes to save us, because at first the signal is so small you would never think there's any hope. But nuclear physicists are magicians, as we will now see. So now this takes us to about 18 years ago, 2004, where these folks who were in Germany and in Munich used the device I just showed you and made a measurement of this object, which is from the bottom of the ocean. And this thing is called a ferromanganese crust. So these things are found in the Pacific Ocean, and it won't take me long to tell you what I know about them. So what happens is there are rocks on the bottom of the ocean that act as a substrate, and they like to grab material from the water column, which literally they chemically bonds to the rock. And it forms this crust of material that grows very slowly over time. And these things particularly like to grab iron and manganese from the water. And this crust then is mostly made of iron and manganese, which is why they're called ferromanganese crusts. And they grow very slowly, 2 millimeters per million years, which is an incredibly slow growth rate, which turns out to be good for us. So, and this rock you're seeing, there's a coin next to it. The coin is about this big. It's a little bigger than a quarter. And so this is a rock you can hold in your hand. And as you go down, every few millimeters, you're going back 1 million years. So this is sampling the past few million years. And so these guys, Kani et al. Use accelerator mass spectrometry to look for radioactive iron as part of this ferromanganese crust. And here's what they found. Okay, so what I'm showing you here, the horizontal axis is time before present. So as they dig down, they're looking back in time. And so the time is shown here. So 2, 4, 6, 8, 10 million years ago, corresponding to deeper and deeper. And then vertically what I'm plotting then is the amount of iron-60 that they find. And there are two features that jump out. This noisy set of points is noise. So this is just their background. Actually, the background at the time. They've gotten better since. That's the background at the time. And the background for the experts is due to the stable isobar, which in this case is nickel 60. So if they only saw this, this is just noise. This is not a real signal. That's just a limit of their ability to measure. So that would be boring if that's all they found. But of course, that's not all they found. They also found this amazing little pulse. And so there we go. So Homer's happy. We're happy because those are our green bananas. This is live, not decayed, radioactive iron at the bottom of the ocean. And so we find this beautiful pulse. We can say when it is. It's somewhere between 2 and 3 million years ago. And the thing that might be hard for you to read here is the signal is tiny. The amount of iron-60 compared to ordinary iron, so the isotope fraction, is 2 parts in 10 to the 15, which is why this technique is just amazing. Accelerator mass spectrometry is amazing. It's like magic. Although people who do it want me to assure you it's not magic. They work incredibly hard to make this happen. And so, yeah, and here's another picture of the accelerator that did this. And this is Jenny Feiga, one of the researchers in the field for scale. So, this is not a tabletop experiment, but it's amazing you can do this at all. Okay. So we've done it. We found live iron at the bottom of the ocean. Something put radioactivity on the bottom of the ocean. That's amazing. And so what can we learn? Well, one thing we can do is we can say something about actually how far away the supernova was. And here's how we do this. What we measure is some number of iron atoms per square centimeter. So it's like a surface density. So atoms per square centimeter in our crazy bottom of the ocean sample. Well, what determines that? Well, the idea is that there's some amount produced in the supernova. It gets flung out into space, and the further away you are, the less you receive. And the amount you receive, it's just the inverse square law. It's just the usual argument for the inverse square law. So the amount you receive, the surface density, then just depends on the amount the supernova makes. That's called the yield, and then the square of your distance from it. But we measure the amount of iron-60. We don't have direct measurements of the yields, but we have our theorist supernova simulators can calculate that for us. So through the miracle of modern algebra, we can turn the problem around and solve for the distance in terms of the iron-60 we measure and the supernova yields. And so we have some of the world's experts in supernova cosmology here. You've probably heard about luminosity distances. This is exactly the same argument, except here, in playing the role of a flux from a supernova, we instead have this radioactivity surface density, and to play the role of luminosity, we've got this yield. But it's exactly the same idea, so I call it the luminosity distance. Sorry, it's normally called a luminosity distance. I call it a radioactivity distance. No one else calls it that, but let me have my fun. We always thought it was a supernova, but I had this excellent student, Brian Fry, who said, no, we should really look at everything that makes iron-60, every astrophysical source, and see which can do this. Let's just be agnostic and let the data tell us. So core collapse supernovae, they definitely can make iron-60. It turns out type 1a supernovae, and you would have heard about these as well, those are these exploding white dwarfs. Those also can make iron-60, although not nearly as much. AGB stars are stars that don't quite make it all the way to be a core collapse supernova, so a little lower mass, but they still can produce iron 60. And also neutron star mergers, which you probably heard about. So when neutron stars collide, they're very neutron rich. They make all kinds of radioactivity, including iron 60. And actually an impactor can do this as well. My student Jesse Miller looked at this, and the long story, it doesn't actually work, but that's also a candidate. So what I'm going to do now, this is now the most complicated plot I'm going to show. We're going to go play whodunit. So we're going to calculate this radioactivity distance for all of these different sources. So for every source, we're going to ask, what distance do I need to have this source? So I have my list of candidates. So this is my lineup of suspects. And then I've got this busy looking plot. Let me explain the plot. So on the horizontal axis, it's the mass of the thing that's producing iron 60. So for example, we have a supernova of mass 15 solar masses, 19 solar masses, 25 solar masses. I put it in this formula and I work out the distance I need to have that object to make the iron 60 that I observe. For example, the 15 solar mass supernova, I needed to have it about 80 parsecs from us. And again, 1 parsec is the nearest star, so this is all really close. Okay, and then the blue things are supernovae. I've got AGB stars here. I've got various objects. And so now, before we interpret this, there are some general regions of the plot to pay attention to. The vertical axis is how far the object is from us. And so that's the distance. And up here, the distance, when it's really large, the distance becomes so far, it's not plausible that the explosion could deliver the material to us. So if we live up in this region of the plot, the iron 60, there's no good astrophysical way to make the stuff arrive here. So if the points are up here, that's a problem. So that's kind of too far. On the other hand, we don't want it to be too close either, because if it's really close, if it's within the kill distance, then it should actually cause a mass extinction on Earth. And so I'm not kidding. The data for this is you look around the room and say, are we dead? No, we didn't undergo a mass extinction 3 million years ago. And so that excludes this region. And so the sweet spot is in between. So with that in mind, let's now go through this. Let's look at some of these sources. So here's a type 1a supernova, like we like to do supernova cosmology with. Well, they're great for supernova cosmology, but they're really bad at making iron 60. So they make tiny amounts of iron 60. They basically aren't very neutron rich. And so the amount of iron 60, to explain the amount of iron 60, you need them to be incredibly close to the Earth, so close they wouldn't just cause a mass extinction, they would sterilize the Earth. So that's out. Next, we've got what's the kilonova, which is these neutron star mergers. Same thing, they don't make very much iron 60. They actually make things more massive than iron 60. And so we can actually rule them out on that, as well as rates are a problem. So they're gone. Next are these AGB stars. These are things that are not quite massive enough to be supernovae. And actually, in terms of distance, they're perfectly acceptable. There certainly are AGB stars at these kind of 10 to 100 parsec distances. But I put a little dotted line here because it's not actually clear that they can get the material to us. They emit their iron 60 in gentle little breezes that are going to be hard to deliver from at this kind of distance to the Earth. So we actually don't think those work either for other reasons. So impactors are also out. And so the only thing that's left here are, in fact, core collapse supernovae, which are these points in blue. And so it looks like really what we have are core collapse supernovae. But we learn more than that. We also get a sense of the distance. And the uncertainties are large because it turns out it's hard to calculate how much iron 60 a supernova makes. But what we see is we get a distance somewhere between 30 to 150 parsecs, which is quite close to us. But the beautiful thing is it's in the sweet spot. It's not so close that it would kill us, not so far that the supernova material would never reach us. So that's quite encouraging. And the other reason this is encouraging is this whole calculation did not have astronomical distances built in. So I took the amount of iron 60 I measured on the bottom of the ocean. I needed some number of iron 60s produced by the supernova, and I get a distance. Astronomical distances weren't built in. I could have gotten centimeters or gigaparsecs, but instead I get something right in the interesting range. So, and that's what this blah, blah here is supposed to say. So that's all very encouraging. Okay, so that's where we were basically until a few years ago. In 2016, we had up till then we had some data, but in 2016, the floodgates opened. And we had a bunch of new data from new probes and new sites. And now the subject has become really interesting. So first of all, there were more measurements in these crazy ferromanganese crusts I tell you about that live in the bottom of the ocean and slowly grow this crust of iron and manganese. And that's a nice consistency check. But then there are now also measurements from sediments at the bottom of the ocean. So this is a picture, this peanut butter looking stuff is from a drill core at the bottom of the ocean. It's been cut in half, and geologists study this for all kinds of reasons. And there was a search for iron 60, and lo and behold, iron 60 is found here. And these things are interesting because they grow much faster. They grow a millimeter per 1,000 years, still an incredibly slow rate, but much faster than the crust. And so the signal is more dilute, but if you find it, you can get time resolution. There's also a whole story about magnetic microfossils. Ask me after the talk about magnetic microfossils. Okay. If the signal is on the Earth and we get hit by supernova debris, then the moon, it's at the same distance. It should also get hit by supernova debris. So you would hope to see iron 60 in lunar cores. And in fact, it has been found. This is Alan Bean in Apollo 14. So it's right after Apollo 13, and this is him taking one of the samples that was measured. And iron 60 has been found as well. For the experts, actually the moon is being hit by cosmic rays, which make iron 60, so it's not enough to show that you have iron 60 on the moon. You have to show there's an excess over the cosmic ray production, and that's what they did. And if you ask me, I can say more about how they did that. Also, cosmic rays themselves contain not only protons, but other elements. And it was also shown that cosmic rays contain iron 60, undecayed iron 60. And once again, it requires a local nearby source. And so cosmic rays also contain iron 60 or additional evidence. And actually, very recently, a few years ago, iron 60 was found in Antarctic snow, but modern Antarctic snow. So snow from the past 20 years. And so at a smaller amount, but that means there's still a flux of this stuff coming on our heads even today. And there's even been a candidate for what star exploded. There's a runaway neutron star that's zooming across the sky, one of the brightest neutron stars in the sky, a pulsar. And if you track it back to where it was 3 million years ago, it goes to one of the candidate star clusters where we think the supernova might have come from. And most importantly, we've now also had new isotopes. There's been searches for aluminum-26 and manganese-53, but most importantly, there's now a detection of plutonium. And I hope to have a little time to talk about that. So a lot of new stuff has happened. So here's the lay of the land. So now this is a map of the Earth showing you all the places where iron 60 has been detected. And so you can see it's been detected in all around the Earth, in the northern hemisphere, southern hemisphere, and by different groups using different measurement techniques or different instruments. And it's also seen in Antarctic snow. It's also seen on the moon. So now there's quite a bit of evidence. And so now this is a data compilation by my excellent now PhD graduate Ada Ertel. The data I already showed you is here. Here's our nice, beautiful pulse of iron 60. That's the original data. Now let me show you what it looks like with all the current data. So these are all the current data. And so this plot is way too busy and too many colors to take in. And that's actually the point. This is just supposed to be shock and awe, showing you that every one of these different colors is a different measurement. There are different groups represented, different labs represented. So this is, there's now quite a compelling amount of data. But it's too much to take in here. So let me take it apart for you. So first, let's look just at the crusts. So I mentioned this original ferromanganese crust, that's in red. All the new ones are not in red. And what you see is there have been many such measurements, and they all agree that there's a signal 2 to 3 million years ago. So everybody agrees that there's definitely a signal there. There have been some hints in the past, and it's a little bit hard to tell. I'll show it better later, but now there's good evidence. There's another signal around 7 to 8 million years ago, so a second signal. So that's pretty cool. To blast. And it's not surprising there too, because remember, supernovae are massive stars are social. They like to live around other massive stars. So it's not surprising to see more than one signal. Then using these sediments, we now have better time resolution because these things grow faster. So you can use the signals more spread out over time. And there's two different groups on different parts of the Earth where the fallout is different. But the important part is, so they see different amounts because of the differing fallout, but what they both agree with, and these are two different groups, they both agree that the time scale is quite large, that the signal rained on our head for 1 million years. And my student showed that this is not a geological effect. This is real. This is astrophysical. And that's actually, there's a whole story here, which you can ask me about. That's actually, remember I showed you the blast wave only comes over us for maybe 100,000 years, which is 1/10 of this width. So we have a whole story about why we think this width is coming about, and we think this actually has to do with dust and supernovae. I got a whole story I can tell. Yeah, ask me after the talk. I can tell you about this. I just want to to emphasize something that I was just alluding to, that we found a second pulse. So in 2021, Wallner and company looked at another one of these crusts where we'd seen the signal before 2 to 3 million years ago. I'm plotting it two different ways here. This is the iron ratio, this is the flux, and the flux goes up and down. We see this nice signal. But then they looked further at an earlier time, and they also find another pulse here. So we've got another pulse which represents a second explosion. And the signal is of comparable strength. It's a little bit smaller total integrated flux, but it's similar. So that would suggest a similar distance, particularly because not all supernovae have to make the same amount of iron 60. But okay, so what does it all mean? How are we doing on time?
So we have, you brought out 10, 15 minutes.
Great, perfect. Okay, great. So now let's talk about what it means. So I already talked about the supernova distance, so how we can use the amount of iron 60 to take a radioactive distance. But now there are other games we can play because we have other isotopes. And I want to tell you about plutonium. So plutonium is super interesting for many reasons. One, it has a long half-life. So it has a half-life of 80 million years. So it goes much further back in time than iron 60 does. Iron 60 only has a half-life of 2.6 million years. But plutonium goes much further back in time. So if we're interested in ultimately connecting this to mass extinctions, which happen tens to hundreds of millions of years ago, plutonium is a good candidate, iron 60 is not. So plutonium's great that way. But it's also interesting astrophysically because it's only made in the R process, which is this is the case where we know the nuclear physics, but we're not sure where it occurs in nature. So the nuclear physics is you need a whole bunch of neutrons, as you would expect. This is a very neutron-rich, very heavy element. So you need a whole bunch of neutrons, and they need to blast material over a short period of time, like a second, so we can build up really heavy elements before anything has a chance to decay, and that's how we can make these super heavy elements. And those kind of extreme conditions, there are only two real sources that we know about. One is the merger of neutron stars, which after all are made of neutrons, and when they collide, in the collision and the resulting explosion, these R process species are produced abundantly, and they, of course, these things also produce gravity waves, which we saw, and there's this beautiful event that we saw both in gravity and light. And from the afterglow of this explosion, it's not a definitive proof, but there's very strong indirect evidence that a lot of R process was made. The exact species we don't know for sure, but it's very clear that this thing was radioactively powered by the R process. I'd say that's very strong evidence, I would say. But there's another environment that can potentially make the R process, and that would be massive stars, core collapse supernovae. The funny thing, though, is supernovae are not as neutron-rich as neutron stars, and a sort of standard supernova, for the experts with a standard neutrino-driven wind, struggles to make very heavy R process species, but plutonium is like the heaviest thing there is, and a standard supernova shouldn't make plutonium at all. Now, if there's a little bit of non-standard neutrino physics, or if the supernova produces a jet, which it seems like some supernovae probably do, then there's a chance it can make plutonium. So, but it's certainly not all supernovae, but there are some that can. And it's also clear observationally, for a number of reasons, for a number of pieces of evidence to tell us that the R process sources, whatever they are rare. They cannot be most supernovae, but it could be some supernovae. So we have this puzzle. We don't know if it's from kilonovae or supernovae, this R process and this plutonium. And then into 2021, we've had this detection in the deep ocean crust. And so with some former students, we've been looking at what does this mean? And so we'd like to sort out, what is this plutonium from the bottom of the ocean? What is it telling us? And the stakes are high because they tell us about the origin of the heaviest elements. Are they coming from kilonovae, from neutron star mergers, or from exploding supernovae? And the test here, so how do we tell if they made the plutonium we already observed? But it turns out if you make plutonium, that's the very heaviest of the heavy elements. So if you make plutonium, you make everything lighter than plutonium, and including other species that are radioactive, which remember are my green bananas. And it turns out that the supernovae and kilonovae have very different predictions for everything other than plutonium, because the supernova struggles to make plutonium and has a better time making stuff lighter than plutonium. So it has high abundances, for example, of iodine, 129, zirconium 93, hafnium 182, these species here. For the kilonova, that's the stuff in red. For the kilonovae, they do a better job making very heavy things, and so they don't make as many light things along the way because they're very good at going straight up to making very heavy things. So there's a different prediction for the amount of the lighter radioactive R process species. So for example, you see iodine here, we make a lot more of it in the red supernova points than in the blue kilonova points. And so the ratio of these species to plutonium can distinguish among these models. And the good news is, and that's something that we can hope to observe, but we don't have, we don't really have dedicated measurements at all, but actually there already are some deep ocean measurements of iodine that were not done for this purpose, but they exist. Unfortunately, the crust isn't dated. It's one of these crazy ferromanganese crusts. It's not dated, so I can't tell you what the time is. I can just tell you the depth. But the interesting thing is if we assume a sort of typical growth rate, we can sort of show what would happen if we had a time scale on this. We could put various constraints. And actually, in this case, the supernova models generally actually make too much iodine. It actually favors the kilonova. So we really would like there to be measurements of all these species, but iodine would be actually the most favored one. And you can do this with accelerator mass spectrometry. And this would be a new probe of the origin of the R process. I have a remaining minute. Want to tell you about maybe something that's maybe more sort of up close and personal in terms of our sun's place in the cosmos. So it turns out another aspect of our supernova is that it will affect our local environment. And it turns out the sun lives in what's called the local bubble, which is a region of hot rarefied gas. So there's sort of an artist conception here. This is a simulation. And this has been known for quite a long time, since the 70s and even some hints earlier. And this is a cavity that's huge. It's 50 parsecs and more on a side. And the people who study this, independent of this iron 60, said, look, it's the result of multiple supernovae. And in fact, you need something like 10 supernovae or more in the past 10 million years. And so the idea then, the iron 60 would be, these two pulses that we see would be from a couple of the more recent and nearby events. And there are specific star clusters that people have suggested, which are about 50 and 100 miles away. And the Earth is moving relative to the bubble, and our transit of the bubble wall is another way to understand this, the fact that the iron 60 took 1 million years to rain out. All right. So the evidence for the supernova is actually all around us in the form of this local bubble. All right. Let's see. How are we on time?
You got about 5 more minutes if you want to go that far.
Okay, so if I got 5 more minutes, then one other thing, this is like sort of for the astro people, there's something that's fun about this, is that we hope that we think this might actually tell us something about dust and supernovae. If you remember the story, the supernova blast doesn't come all the way to the Earth, and so the supernova material comes to us in the form of dust, which can go the rest of the way from 20 AUs to the Earth. So the supernova material comes in the form of dust. And so we're imagining our iron 60 finds its way onto dust particles as the supernova produces a bunch of dust when it's born, and then the dust moves within the supernova remnant, which in general will be magnetized. And so my excellent student did a simulation of the motion of dust inside the supernova explosion, the bubble that it makes, the supernova remnant. And what he found is that these dust particles, they're microscopic, but still much bigger than atoms. They're sort of micron sized. So compared to the atoms, they're like cannonballs. So in this expanding bubble of this supernova, they're like cannonballs. So they actually blast through, and if they're not too small, they actually if you ignore magnetic fields, they actually go outside of the blast. The blast decelerates as it encounters interstellar material, and it slows down. But the dust actually doesn't. It's like a cannonball and punches out in front of it. And other people had simulated that too. But then my student said, well, look, these dust particles should be charged. There should be magnetic fields, at least in the interstellar medium, if not in supernovae. So let's see what happens if we turn this on. And here's what happened. We found that the material, the dust, moves along in radial trajectories. It's born in the supernova at high speed, moves along. And then we found this interesting thing when it encounters the magnetic fields, which has been compressed by the supernova blast. The magnetic fields act like a magnetic mirror, and they turn the dust around and it bounces back. So they not only don't punch out ahead, they actually get trapped within the supernova. And it bounces around. And here's a little image from one of our simulation results. And you can see the dust starts at where the supernova is and then bounces around as it encounters this magnetic bubble it lives in. And the dust will keep bouncing around, living its own life. Then it also will be slowed down due to drag forces. A little bit will be sandblasted due to sputtering, and then eventually comes to a stop. And the timescale for that is quite long. That's 1,000,000 years. And we think that's the origin of the 1,000,000-year timescale for the rain out of this material. And so we think then this iron 60 is telling us something about the production and evolution of dust in supernovae, which is a subject of interest beyond just nearby supernovae. All right. So with that, I know Louis is getting nervous and you've been very patient on Zoom. So let's wrap it up and give you my outlook. As you can see, all the collaborators who made this work possible. So the take home point here is that live iron 60 has been seen globally and on the moon. And there's all kinds of signals. So I've got a long list here. We see it in deep ocean crust, nodules, which are light crust but smaller, sediments, and cosmic rays. We see a beautiful pulse 2 to 3 million years ago. Everybody agrees with that. There's now another pulse 7 million years ago. We think we have some understanding of this iron 60 duration. There's a lunar signal. If you ask about it, that potentially can say something about directionality. Ask about that. We found plutonium, but it's not yet clear whether it tells us we've seen a supernova or a kilonova, but we have ways of testing this. And this all should be a fossil of the local bubble, this cavity that the sun lives in. So this is the birth of supernova archaeology, where deep ocean material tells us about supernovae. And what's so much fun about this is that it's so interdisciplinary. So this the top list is all the astrophysical subjects that are touched upon by nearby supernovae, all the way through astrobiology. But it's also fun, it even goes beyond astrophysics to heliophysics, the study of the bubble that the sun lives in. And you've seen that nuclear physics is critical to this, and there's a role for geology and even potentially biological evolution. So I wouldn't want to leave you with the impression there's nothing else to do. So there are plenty of connections and opportunities for future work. So first of all, I mean, it's just amazing. We see these live isotopes, which tells us they somehow made it from a star to the bottom of the ocean into the moon. And this has implications for how the elements are made, nucleosynthesis, particularly supernova nucleosynthesis and our process nucleosynthesis. It tells us something, I think, about the production of dust in supernovae. It talks about how this bubble we live in, this heliosphere, would be very different back in the past, and we think there might be opportunities for signatures of that. The supernovae accelerate cosmic rays, which then would be we'd be very near the supernova accelerator. And I already mentioned there's a potential connection with a neutron star. Oh yeah, and for experts, this whole enterprise of nearby supernovae and looking at these isotopes is very similar to the study of pre-solar radioactivities. But here, in a way, it's better because we still can look at the environment and have an idea what the environment is like. So there are also experimental and observational challenges. So we would love to do more of this accelerator mass spectrometry to look for these other sort of million-year medium-level isotopes, particularly iodine-29. But I've listed some other species here that are of interest. Hafnium-182 would be very good. Other media, ice cores. For a long time, the ice core data from the South Pole didn't go back far enough. It only goes back, most of it only goes back less than 1,000,000 years. But there have been some recent discovery of ice core material that goes back even to 2 million years and even up to 3 million years. And so potentially that might be very interesting as well. And we'd love to go back to the moon and get some more lunar data, particularly different locations on the moon, because we think that's very interesting. I can tell you more about why. And that's not a pipe dream, because within the next week or two, we hope to have the next U.S. mission to the moon, the Artemis mission, the first uncrewed robotic launch will happen in a few weeks and go to the moon. and come back. And actually, there's a robotic Chinese mission, Chang'e, which has already brought back samples from the moon and already landed on the far side of the moon. And there's more of this coming, and so that's a real possibility to get more lunar data. And there's lots to do with that. We can also learn more about, like I said, the archaeology of the local bubble. There's more to be studied there. I didn't mention this, but there's work on the potential impact on the solar system, biological damage, not a mass extinction, but biological damage from this supernova. And going back to even earlier epochs, once we see that there's real evidence that nearby supernovae do occur, the one 3 million years ago, 7 million years ago, wasn't close enough to be a mass extinction, but in the more distant past, it's entirely likely such a thing has occurred. And we actually have a suggestion for a particular extinction that we think might be due to a supernova. So there's lots of interesting stuff yet to be done. So stay tuned. And with that, I thank you for your time and attention. I'm happy to answer any questions.
Okay, thanks a lot, Brian. That was incredibly entertaining and really, really interesting. So we do have some time for questions. So maybe if we have some questions, maybe you can start by raising your hand from the audience, and I can call on people. So Grisha, go ahead.
Thank you, Brian. Indeed, very interesting talk. So you are talking about iron 60 fluxes from the supernova explosions, but the question is, so what are the uncertainties? Because to estimate distance and so on, you need to know the yield, right?
Yes.
So could you please comment on uncertainties for the iron 60 yields?
Yes. Great. That's a great question. That's exactly the right question. And the uncertainties are quite large. The iron 60 measurements themselves, are very difficult measurements, but those actually aren't the dominant. Like when I showed you the distance to the supernova, it's actually we don't know the amount the supernova makes. If you think in terms of luminosity distance, we don't know the luminosity very well. I have a plot, but it'd probably take me too long to find it. But I can just tell you that iron 60 is one of the hardest things to calculate because it's not one of the main products of a supernova. To get iron 60, supernovae love to make, they don't actually make iron 56 as much as nickel 56, but to get to iron 60, you have to take iron 56. Actually, it's generally the iron the supernova was born with, and then it has to add neutrons. So it has to add 4 neutrons to get to iron 60. So you can think of it for the experts, it's like a little bit of an S process. And of course, every time you add a neutron, there are other competing processes to get all the way up to 4 neutrons. That's why there's not very much iron 60 that comes out. And it turns out the yields from different groups are all agree sort of within an order of magnitude, which is good, but they, in detail, they don't agree with each other, because this is a very difficult element to calculate. And so that alone, introduces, a substantial theoretical uncertainty. In principle, there are other ways of getting a sense of this, because, for example, iron 60, when it decays, also makes a gamma ray line that you can measure. Not Lewis gamma rays, which are like GeV gamma rays. This is a nuclear line, so these are MEV gamma rays. So it's measured not by Fermi, but by integral or Comptel. And we actually see iron 60 from the sky. So the galactic disk glows in iron 60, and the data is not good enough to pick out individual remnants so you can work out the yield. But from the glow, we can see that the average yield is about what you get from the theoretical models. So it's all sort of broadly consistent, but the uncertainties are still large, which is why my distance errors were very large, exactly as you say. And so, what we'd really like if we had better gamma ray data, that would be a nice way to empirically measure these yields. And it would be interesting for many other reasons, but that's one of the reasons I would love a gamma ray telescope working in the MEV.
Thank you.
Great, thanks. We have another question, go ahead.
Yes, you mentioned that the solar system is in a local bubble, and presumably the local bubble is swept out by supernova explosions.
Yeah.
But then, according to you, if your iron 60 due to supernova that's only 2 million years ago, you are saying that the bubble is only 2 million years old?
So yeah, thanks for the question, because I went over this very fast. So this bubble is quite large. And so the people who study this bubble, before we did any of this, before the iron 60 was even measured, they say to get the bubble this big, you need more than one supernova. You need at least 10 supernovae over the past 10 million years. So the iron 60 then would be this 3 million year supernova, would be one of the more recent ones, but there would be even earlier ones. And indeed, like I showed you, we now have evidence for a second one at 7 million years ago. And we'd like people to keep looking because there may even be further evidence earlier, because there should actually be quite a number of events. So because it takes more than one supernova to make the bubble as big as we see.
But even if the supernovas that would in the past 10 million years, that is still quite recent. You're saying the bubble is still a quite recent phenomenon.
Oh, yes, that's right. This bubble is something like 10 to 20 million years old. It's not so clear exactly how old, but it's something like that. Yeah, but it's a transient feature. We do not always live in a bubble like this. It's just true that we live in one now, but our whole life around the galaxy is not always spent in one of these bubbles. It just happens we live in one now. But that's an observation. That's not just some theorist thing. We observe the low density, high temperature of the bubble. That's where we happen to live. So we're in a tough neighborhood right now.
No, we're in a good neighborhood, actually.
A good neighborhood, right? Yes.
Okay, thanks.
Okay, I'm Hans Schüssler,
Oh, okay.
and I would thank you very much for this very nice talk. And I am particularly interested about the moon, because we have this Artemis coming there and going there, and now we have radioactivity, and you listed some of the elements. I was wondering, plutonium and uranium is very abundant here at the nuclear test site or somewhere. Yeah. But I'm very surprised that we have these radioisotopes also on the moon. Can you tell us a little bit about this more?
Yes. Yeah, and in fact, you exactly put your finger on one of the reasons the moon is so interesting. Exactly. So, for example, this plutonium that I told you about, which is so exciting, that paper, they spent a very long time on that paper. Years after they measured the plutonium, they spent all their time convincing themselves that they weren't being fooled by bomb debris on the Earth, because that measurement was at the deep ocean. And exactly as you say, there are, the polite term is anthropogenic sources, which is a polite way of saying bomb debris and nuclear accidents make plutonium. And they actually had the top of their sample, their plutonium sample actually had plutonium-30, not 239, which is not from a supernova. It's short-lived. It's bomb debris and actually from probably Fukushima as well. But then that stuff trails off as you get deep in the sample, where you just have the plutonium-244. The beauty is, as you say, the moon shouldn't have bomb debris on it. If it does, that certainly is interesting in its own right. But presumably there's no bomb debris on the moon. So as long as the samples are taken carefully that aren't contaminated by Earth bomb debris, that's one of the great things about the moon, is there ought to be a nice, very clean plutonium signal there. And we also think even something like curium might be, curium-247 would be interesting to look for. And again, bomb debris would be a problem on Earth, but the moon would be perfect for that. So yeah, that's one of the great things about the moon, is it lacks all of these contaminations. There are other problems with the moon, but cosmic rays can produce some things on the moon, but the cosmic rays do not produce plutonium or curium on the moon. So that's why it's so beautiful. It's a perfect place to look for those.
We had the Apollo missions, more than 30 years ago, and there was nothing happening about the moon. And so this recent activity is very, very fascinating. It's the closest heavenly planet to us, and all these wonderful things. So thank you very much.
I completely agree.
Yeah. Thank you.
I'm a big Apollo fanboy, so I'm really glad that we're going back. If you're not familiar with, by the way, Artemis is an upgrade, because now women are allowed to go along as well. So they will be the first woman on the moon. So we can also look forward to that.
See. Yeah.
We have another question from Carl. Go ahead.
So I'm intrigued about the connection to the mass extinctions.
Yeah.
What happened 65, 66 million years ago, and it wasn't a supernova.
Correct.
But there were 3 or 4 mass extinctions 200, 250 million years ago. I don't remember the dates and the precise numbers, at least one of which was even bigger than
that's
the
right.
one that killed the dinosaurs. And
that's right.
I've seen suggestions that a supernova may have caused one or more of those, but is there any chance that far back that we could actually find conclusive evidence one way or the other?
Bless you. Check is in the mail. Like, oh, that was not a setup question, I promise. And I will spare you showing a slide, but I'm having to hold myself back. So yes. So let me say a few things about that.
You can show a quick slide if you want. No one's preventing you, if it helps.
All right. So, but while I look for it here. So yeah. So first of all, let's see if I can find it quick enough. So first of all, you mentioned the yeah, maybe I'm not going to find it quick enough. I don't want to get too distracted by this. Yeah, all right, let me just tell you about it because it's gonna take me too long to find it. So let me just go back to where we were. Okay. Yeah, I'll let all this stuff play out. So first of all, you mentioned 65 million years ago, of course, is when the dinosaurs died, famously, as we all know, and we love to tell the children. You know, I loved that when I was a kid. Of course, that was an impactor, and for sure, the geologists will say there's probably the dinosaurs are kind of on the way out anyway, and that was kind of the final coup de grace. But everyone agrees there was an impact. And we found the crater and the radioactive dated. It's beautiful. 65 million years ago. The interesting thing is the Alvarez paper that first suggested an impactor. This is 1980. It was before the crater was found. They actually thought it might be a supernova, and their paper has two whole sections going through, and they say they were very smart. They said, oh, you should look for radioisotopes, and they actually did, and said, oh, but we don't find plutonium. And so they actually looked for plutonium in that sample, failed to find it. And at the time, everybody thought plutonium had to be from a supernova. So it can't be a supernova, got to be an impactor. Now we think differently about the plutonium. It might not be a supernova product, but they still made the right conclusion, it had to be an impactor, and the crater was later found. So that's cool. But in fact, what I mumbled about here is we actually had a suggestion right after the pandemic began. It was an all-pandemic paper. We caught when there was a geological measurement at the end of the Devonian period. As you say, there are multiple extinction periods. The dinosaurs were the least bad. There are 5 major mass extinctions, and the 4 prior to the dinosaurs were worse. And one of them is the Devonian. And the Devonian, there's a whole story. It's sort of this slow die-off, which is probably due to sort of environmental effects. But right at the end, there are these really punctuated extinctions where a whole bunch of stuff died really rapidly. And there's a couple of such things. And a geologist was studying this and found that in one of these really punctuated periods, there suddenly was a big loss of ozone, stratospheric ozone, which they see because it damaged the little plant spores. And then they recovered afterwards. And they had some suggestions to do with geological reasons and volcanoes, which they ruled out, but they had some other ideas. But they didn't mention anything astrophysical, so we wrote a paper saying, could it be astrophysical? So could it be a supernova? We don't know for sure it's a supernova, but could it be? And one of our suggestions is to look for radioisotopes. That would be the signature. There's some other sort of geo predictions, but the sort of real sort of smoking gun would be plutonium, if our supernova was kind enough to make plutonium, but again, they might not all do that. Or it turns out samarium 146 is long enough lived that there's still some hope you could find that, and that's more likely, that's more or less guaranteed to be made by a supernova. For the experts, it's a P process element. So at the moment, so that's still an open question whether those can be found. Whether there are suitable samples where you can find those things, but there's at least a way to tell if that was due to a supernova.
Cool, thank you.
So we would love for somebody to go look for that stuff. Yeah.
Very good. Any further questions? Can I ask the Liberty about oh no, wait, actually no, Phil, go ahead.
I mean, you can go first if you want.
No, mine was kind of out in left field, so but you go ahead. Okay. I can ask.
Well, mine are particularly nerdy. So I know that in the past, people have suggested looking at, for example, nitrogen 15, oxygen 18, some stable elements for overabundances for looking for signatures for core collapse supernovae from the helium burning shell. And I'm wondering if you said looking at stable isotopes is not so good, but are there possible stable isotopes which could be helpful here?
Yeah, unfortunately, this is I keep kind of redoing that order of magnitude calculation because I keep wanting that to be true, and it's just not. In fact, related to that, like I so would like that to be true, but yeah, it just because remember the supernova signal is tiny. Remember, it's a microgram per square centimeter of bulk material, and even less for any specific isotope. And that just always the terrestrial background just gets you every time. Even to give you an idea, we were hoping that maybe uranium isotopes might work because, the Earth obviously contains uranium, for good or for bad, it does. But we were hoping maybe, there the supernova signal could be, because some of it's decayed maybe. And even then, the terrestrial signature of both uranium isotopes is just too big, even for, even that overwhelms the supernova signal. So stable stuff just doesn't work. We tried hard. Oh, is there someplace we can look? And it's just, it's the terrestrial signal is just too big, which is another way of saying that the supernova signal is really small. That's why it's got to be radioactive, because otherwise the background is just kills us. So I'm sorry to say that. I wish that were not true, but it just seems to be.
I mean, it's unfortunate, but I guess that was the case. So
yeah.
Thanks.
A very, very quick question. What asteroids? You talked about the moon and you talked about Earth.
Yeah.
Is there anything that we learned from asteroids?
Yeah. So yeah, my Jesse Miller here looked at this, and then and actually one of the in one of the experiment papers they also looked at it. So yeah. So the idea is. I mentioned that in the moon, you get some iron 60 just from bombardment by cosmic rays. So it's made by spallation processes, fragmentation processes by cosmic rays. And they have to spallate nickel. And so on the moon, you had to show that what you found is in addition to the spallation component, which they did, and I can tell you more about how they did that. But that same thing would occur on the surface of an asteroid. So the surface of asteroid would get baked by cosmic rays. And then when it collides with us, as it falls down, the outer layers get burned up, then the stuff gets distributed over the Earth. And if it impacts hard enough, it also gets distributed over the Earth. And then that's another way to explain the iron 60. Because of course, that's what we just see. We see this pulse of iron 60. But to do that, you can calculate how big an impactor you need. And it turns out it has to be, to explain that iron 60 signal, you actually need a really big impactor. It needs to be big enough that it actually has to be bigger than the KT impactor. It has to be bigger than the thing that killed the dinosaurs. And once again, you look around the room and we didn't suffer something that dramatic 3 million years ago, so that doesn't work. And we actually showed even if you have multiple smaller impactors, then there are other elements you should find, and basically we can also rule that out, so it can't be an impactor. But yeah, you have to check that because all we see is the iron 60. Well, of course, now we see the plutonium as well. And also, once you see the plutonium, it's very hard to make an impactor work because there's no way to put plutonium on it. Cosmic rays do not make plutonium. So plutonium is also a way to rule it out.
Okay, cool. So any further questions for Brian here? Gone a few minutes over, which means everyone's really interested and had a lot of good questions.
Great.
So maybe we'll give, let's thank Brian once again for giving this really excellent talk. Maybe one of these days, definitely one of these days, we'll have him actually visit College Station and give us an update about what
that'd be great. And my cousins will be so happy. Yes.
Oh, that's right. If for only that reason, right? So, okay, so sounds good. So thanks again, Brian, and we'll see everyone else next week for the next week's.
Thank you all.
Thanks, Brian.